ATM, Asynchronous Transfer Mode. Asynchronous Transfer Mode, ATM, is a high-speed networking technology designed to handle both high-capacity data and real-time voice and video. Developed in the 1980s and 1990s, it was intended to be the universal networking standard. Unlike Ethernet, which uses variable-length packets, ATM uses fixed-size cells. This uniformity allows hardware to process data at very high speeds with predictable timing. Key characteristics: Asynchronous Transfer Mode, ATM, is defined by several unique characteristics that allow it to act as a bridge between the predictability of traditional phone systems, circuit switching, and the flexibility of computer networks, packet switching. The following are the key characteristics that define ATM. 1. Fixed size cells, 53 bytes, unlike Ethernet or IP, which use variable length packets, ATM uses fixed length cells. Structure: each cell is exactly 53 bytes, 5 bytes for the header and 48 bytes for the payload. Benefit: hardware can process these small, identical units much faster than variable packets. This reduces jitter, timing variations, which is critical for clear voice and smooth video. 2. Connection-oriented nature. ATM requires a setup phase before any data is sent. It establishes a virtual circuit, VC, between the sender and receiver. Predictability: because the path is predefined, all cells follow the same route, ensuring they arrive in the correct order. Identifiers: each cell header contains a virtual path identifier, VPI, and a virtual channel identifier, VCI, to guide it through switches. 3. Asynchronous multiplexing. Traditional systems, like TDM, assign specific time slots to users. If a user isn't sending data, their slot is wasted. ATM is asynchronous because it allocates slots on demand. Efficiency: if one user is idle, another can use the available bandwidth immediately. Flexibility: it can handle bursty traffic, like a web page download, alongside steady traffic, like a phone call. 4. Advanced quality of service, QoS. ATM was designed from the ground up to guarantee performance. When a connection is made, the user and the network agree on a traffic contract using specific service classes. Service class: full name, primary use case, CBR, constant bitrate, uncompressed voice and video, dedicated like speed. VBR, variable bitrate, compressed video, MPEG, that fluctuates in data size. Abridged available bitrate, general data, uses whatever bandwidth is left over. UBR, unspecified bitrate, low priority background data, no guarantees. 5. High-speed hardware switching. Because the cells are small and fixed in size, ATM switching can be done almost entirely in hardware, ASICs, rather than software. This allows ATM to reach speeds of 155 Mbps, 622 Mbps, and into the multi-gigabit range, which was exceptionally fast during its peak. Summary of differences: feature: traditional packet switching, IP, ATM, cell switching, packet size variable, variable delay, fixed, predictable delay, connection, connectionless, best effort, connection-oriented, guaranteed, primary goal, efficient data transfer, integrated voice, video, and data. ATM cell structure. Every ATM cell is exactly 53 bytes long. This specific size was a compromise between the needs of voice, which requires small cells for low delay, and data, which prefers larger packets for efficiency. Header: 5 bytes contains routing information. Payload: 48 bytes contains the actual data, voice, video, or file fragments. The header contains several key fields, including the virtual path identifier, VPI, and virtual channel identifier, VCI, which tell the switches where to send the cell. The 5-byte header of an ATM cell is dense, with every bit serving a specific purpose for high-speed switching and traffic management. There are 2 slightly different header formats: UNI, user-to-network interface, for the connection between a user and a switch, and NNI, network-to-network interface, for connections between switches. 1. GFC, generic flow control, 4 bits location, only in the UNI header. Purpose: originally designed to manage traffic flow between the user's equipment and the first ATM switch, example to prevent multiple devices on one line from overwhelming the connection. Current status: it is rarely used as originally intended and is typically set to all zeros. In the NNI format, these 4 bits are reassigned to the VPI field to allow for more virtual paths in the core network. 2. VPI, virtual path identifier, 8 to 12 bits. UNI, 8 bits, up to 256 paths. NNI, 12 bits, up to 4096 paths. Purpose: it identifies a bundle of virtual channels. Think of the VPI as a large highway that carries many individual lanes, channels, to the same general destination. This allows switches to route large groups of traffic simultaneously by looking only at the VPI. 3. VCI, virtual channel identifier, 16 bits. Purpose: identifies the specific logical connection within a virtual path. If the VPI is the highway, the VCI is the specific lane. Capacity: 16 bits allow for up to 65,536 channels per path. The combination of VPI and VCI is what provides the unique address for a cell on a specific link. 4 PT, payload type, 3 bits. This field tells the switch what kind of data is inside the 48-byte payload. Bit 1 indicates if the cell contains user data, 0, or management/control data, 1. Bit 2, EFCI explicit forward congestion indication. If a switch is congested, it sets this bit to 1 to tell the destination that the network is getting full. Bit 3, AAU ATM user to ATM user bit. It is primarily used by the AAL5 adaptation layer to mark the last cell of a data frame so the receiver knows when to stop reassembling. 5 CLP, cell loss priority, 1 bit purpose, acts as a discard eligibility flag. Value 0, high priority, the network should try its best not to drop this cell. Value 1, low priority, if the network becomes congested, these cells are the first to be discarded to protect high priority traffic. 6 HEC, header error control, 8 bits purpose, a checksum, cyclic redundancy check, calculated using the first 4 bytes of the header. Capabilities, * single bit correction, it can fix a 1-bit error in the header without dropping the cell. Multi-bit detection, if more than 1 bit is wrong, it discards the cell to prevent it from being misrouted to the wrong destination. Delineation, it also helps the receiver find the start of a cell in a continuous stream of bits. Summary table field full name bits, UNI, primary function GFC generic flow control for local traffic management, often unused. VPI virtual path identifier 8 routing of bundles, paths. VCI virtual channel identifier 16 routing of specific connections, channels. PT payload type 3 distinguishes data versus management cells. CLP cell loss priority 1 identifies low priority cells for discarding. HEC header error control 8 error detection/correction for the header.